Hello, I'm Magnus Halldorsson, and I'll be talking about distributed graph coloring. This is joint work with Fabian Kuhn, Alexandre, Nolin, and Tigran Tonoyan. Now, the graph coloring problem is one of the most classic optimization problems, but it's particularly important to distributed computing, where it forms a particularly elegant resolution of the problem of resource contention. In fact, this was the topic of the first paper that introduced the study of local algorithms. As we know, the graph coloring is the problem of assigning colors to the nodes of a graph, such that adjacent nodes receive different colors. Now, the local model introduced by Nolin in 1987, when he actually was studying the graph coloring problem, we have an n-node communication graph, which is in fact the same graph as the one we will be coloring. And we proceed in synchronized rounds, where each node starts by receiving messages through the edges from its neighbors. It does some local computation, and then it sends messages through its edges to its neighbors. And at the end of this, the nodes announce what colors they will pick. And it better be a different color from the ones used by their neighbors. The measure of complexity here is the number of communication rounds used. In the variant of the model where we restrict the bandwidth of each edge to log n bits per round, we call it the congest model. Now, we might want to use an optimum number of colors, but as we know, that is a very difficult problem. Difficult to optimize, difficult to approximate, hardly at all. And that suggests that it's hard to get a very good handle on. So the core distributed problem is to compute a delta+1 coloring, where delta is the maximum degree. So we want to assign the nodes the colors from the set 1 to 3 up to delta+1. And this is easy to compute sequentially. And usually in distributed setting, just achieving what's easy to do centrally is challenging enough. And it also has the feature that any partial solution can be extended to a full solution. And that is what makes the distributed solution relatively doable. Now, the variant called Degree+1 list coloring, each node is given a list of colors or a palette. And the size of that list is at least this Degree+1. But otherwise, the set can be fairly arbitrary. Now, in delta+1 coloring problem, we're given the colors. Let's say here we have delta equal to 3, so we're given the 4 colors to use: yellow, red, green, blue. But let's suppose that we have already colored some of those nodes. Then the remaining nodes cannot use the whole set because some of their neighbors are already colored. In fact, some of the nodes are restricted to use only small subset of the available colors. In fact, what remains is, in fact, that Degree+1 list coloring problem. And this is a common occurrence. D1LC, as I call it for short, occurs very frequently as a subproblem when solving other coloring problems. It also has the advantage that it's self-reducible. Namely, any subproblem of D1LC is also a Degree+1 list coloring problem. Now, one issue you might think of is that you haven't heard so much about Degree+1 list coloring. Why is it important? It seems like we don't have too many results on it, and which is in fact true. If you look at almost any interesting model, certainly any distributed model, there are hardly any good randomized algorithm for Degree+1 list coloring. There are actually good ones for in the deterministic case, But in the randomized case, there's an exponential difference in what we can do in the local model and in the congest model. And in the congested clique, for instance, we can do delta plus one in constant rounds, but nothing of that sort is known for degree plus one list coloring. And this holds for other models as well. We have quite strong and good results for delta plus one coloring, but nothing for degree plus one list coloring beyond the trivial. So why is that? Is that because people are not interested? It's actually more that there's some intrinsic challenge in the degree plus one list coloring problem that I will get to. Now, our main result is that we can actually solve it in the same time complexity as degree plus one, sorry, as delta plus one coloring. And we essentially achieve an optimal randomized algorithm, modulo some assumption about the deterministic complexity of the problem. For the case when all nodes have degree that at least certain polylog of n, we get very fast coloring. And even for the case of delta plus one coloring, our algorithm provides actually a simpler solution of the most challenging part of those algorithms. Now, the particular innovations in this work are twofold. On one hand, we provide a slack generation theorem, showing how to generate slack in terms of degree plus one list coloring. And this is really was the missing component for the fast solution of D1LC in all these previous, interesting models. Secondly, we give a way of handling the dense nodes by a particularly simple approach. Now, in a follow-up work, we have shown that just about all the above results also hold in the congest model. I'd like to bring to your attention a recent, very interesting result of Asadi Chen and Khanna about delta plus one coloring. It says the following: suppose the nodes in the graph pick a random sample of log n colors. Each node picks that random sample uniformly at random, independently of the other nodes. And now there still exists a delta plus one coloring of the graph, such that each node is constrained to use a color from its sample. And why is that useful? This means that after you perform the sampling, the degree of the graph that's relevant actually really shrinks. Namely, you only need to concern yourself with neighbors that have picked some color in common. And then it's fairly easy to show that the degree of each node becomes at most log square n. Now that means that we've essentially shrunk the graph to semi-linear size, which gives a trivial algorithm for the massively parallel computation model when you have semi-linear local memory. It can also be used to derive constant round semi-streaming algorithm and sublinear time algorithm in a query complexity model for the delta plus one coloring problem. Now you might ask, what about degree plus one list coloring? This was addressed by Alan and Sadi in last year paper, and they managed to extend the result in two ways, both to delta plus one list coloring and degree plus one coloring. But for degree plus one list coloring, they achieved an approximate version, namely within a 1 plus epsilon factor for any epsilon greater than 0. Now it turns out what was missing there was the slack generation result. So if we take our slack generation lemma and plug it into their framework, we immediately get palette sparsification for degree plus one list coloring. And as a result, we also get these algorithms for these three different models mentioned above. Now I'm going to outline some of the core ideas, distributed coloring algorithms. in the randomized coloring algorithms. The first one is very basic. Each node just tries a random color that's available, namely not used by a neighbor already. And this works actually quite well. It gives us a log and round algorithm, just repeating this. But by itself, it takes log n is not fast enough. We want to do something faster. So to do that, we split the nodes into sparse nodes and the dense nodes. The sparse nodes are those that are locally sparse, namely within their induced neighborhood, they have a omega of delta squared pairs of non-adjacent neighbors. Namely, each neighbor has linear number of other neighbors that they are not adjacent to. Now, the nice thing about the sparse nodes is that it's easy to generate slack for them in a single round, and the slack is linear in delta, and this allows us to color those nodes very fast, even in the congest model. Now, for dense nodes are, you can show that they are in fact partitioned into clusters, almost cliques. This is work of Harry, Schneider, and Su from 2016, and actually goes back to work in graph theory by Reed from 1998. And so you can partition these dense nodes into these almost cliques, and the idea then is that within each almost clique, the nodes synchronize their trials. They still try a random color, but they try it in a way so that they don't conflict with other nodes within the same cluster. And that allows us to basically shrink the graph very quickly. Now, in the final case, we have to deal with the low degree case. And there we run the same algorithm, but we just don't get high probability bounds. Instead, we can argue, and this goes back to work of Barenboim, Elkin, Petty, and Su, I believe, from 2010 or so, that showed that the remaining part of the graph is shattered into small components of polylogarithmic size. And this is then, these components then can be solved deterministically. And since the components are small, that complexity is then low. Now, I mentioned slack generation. What is that and why is that important? Slack of a node is basically the number of extra colors it has, beyond the necessary in order to deal with all the competition in the form of uncolored neighbors. So slack is basically the number of colors it has, the size of its palette, minus the number of uncolored neighbors. And if the slack is linear in delta, then in fact there are methods to color such nodes very quickly. Now, but how do you obtain this slack? Well, it turns out if you have sparse nodes, it suffices just for the node to try a random color, and you can then show that they in fact get linear slack with high probability. It's fairly easy to verify that they get that in expectation, and the argument has a lot of dependencies, but this is now a standard how you resolve that. So as long as the degree of each node is logarithmic, you get linear slack for sparse nodes. Now, why is slack so useful? And I'll give a little example here. Suppose you have 3 times more colors than you have neighbors, uncolored neighbors. So you have T over 2 neighbors, 3 T over 2 colors. which means that your slack is then D. And now let's do some thought experiment where we try to estimate the number of neighbors that remain as we basically try a random color in each round. And let's assume, for simplicity, which is obviously faulty, that the expected number actually gives us a worst case bound also, but this actually gives us the correct intuition. Then we can argue that, in fact, the failure probability of a node picking a color that is the same as some neighbor, and therefore it won't get colored in that round, actually decreases doubly exponentially. And therefore, the number of neighbors it has is also goes down doubly exponentially, which means that basically after log n rounds, we're done. We're at least in a case that we can resolve quickly. It turns out actually if you use more powerful methods, if you try multiple colors at a time, then you can actually get this done in log star n rounds. Now in the degree+1 list coloring case, we have some challenges. We would like to do the same, but there is a good counterexample here in the work of Chang, Li, and Petty. They consider this instance where you have a node V, and its neighborhood is divided into two equally sized disjoint cliques. And the two cliques, the nodes in each clique have the same palette, but the palettes of the two cliques are actually almost disjoint. They share only a single color, the purple one. That means that there's no way to generate more slack than just a unit. A unit is not enough to give us very much. So in fact, it's impossible to generate slack for degree+1 list coloring in the usual sense of the term. And there are more complications that I will skip over here, but we were able to get around this with the following result. If we look at the set of sparse nodes, some of the nodes that are shown here in blue actually get sparse in the usual way by running this random color trial procedure. Those that don't, I'm showing here in yellow, they have the nice property that they have a lot of neighbors that are blue. Namely, they have a lot of neighbors in other sparse nodes that are not yellow. A lot of meaning linear in their degree. And what does that give us? Well, that means that we can actually color all the sparse nodes now in 2 rounds rather than 1 round. We first look at the yellow nodes, and okay, they don't have slack in the usual sense, but they have slack in a temporal sense, because the blue nodes, if you have the blue nodes waiting, they're not competing for their colors, and therefore the yellow nodes function as if they had a lot of slack. And then once we're done with the yellow nodes, we can color the blue nodes in the usual way. And that's it. Now, the proof of this is somewhat involves various types of nodes that I will not get into. Some of them are basically, you can argue in the usual way, but there are a couple of sets of nodes that we have to give quite a different treatment. Now, the other case I wanted to mention here is the dense case. So what we want to achieve here is we want to color all the nodes with the same cluster by having the nodes try a random color, but still it's dependent within the cluster, so that nodes within the same cluster receive a different color. Looking from the outside, they function as being random, but on the inside, they're completely dependent. And having them non-conflicting with within the cluster is very useful, because most neighbors, since these are so dense clusters, most of their neighbors are within the cluster. So therefore, their failure probability, picking some color used by a neighbor, becomes quite low. Now the challenge is to actually achieve this synchronization and get the correct random properties. We are able to show that the following procedure achieves this in a single phase. We have to apply this primitive just once. And we do as follow. We pick a leader for each almost clique C. The leader is the densest node in that clique. And then we eliminate the outliers from the C, color them. We can color them because while the other nodes are waiting, they have enough slack to be colored quickly. And which nodes are outliers? Those are nodes that differ a lot from the leader. They differ either in the sense that they have a very different, much higher sparsity, or they have a very different neighborhood. And now, once we have eliminated the outliers, we apply the following very simple rule. The leader simply randomly permutes its palette. And then it sends the colors one by one to the nodes in remaining nodes in the clique. That is to say, it sends the first color in its permuted palette to the first neighbor in the almost clique, a second node in the permuted palette to its second remaining neighbor in the almost clique, etc. And then those nodes try that random color. And well, if no other node picks it, then they are fully done. But if some node picks it, well, then obviously it won't work. And the challenge is to show that this works well. In particular, it's not obvious that the nodes actually get a good color. They might get a color that used to be in their palette, but some neighbor outside the clique already picked that color. Or they might receive a color that never was in their palette because their palette is different from the leader. But this is where the strategy about picking the outliers comes into play. And we were able to show that, in fact, such nodes are relatively few, so that the total number of nodes that remain is only proportional to the slack that the nodes have, because even dense nodes get some amount of slack. And that means that we can now color those nodes by this fast method of Schneider-Wattenhofer. And finally, there's one more trick, which is that extremely dense almost cliques get a special treatment by so-called independent traversals. And this allows us to color the high degree nodes very quickly. Now, in conclusions, we've essentially resolved the question about randomized distributed degree+1 list coloring. But this is modulo the deterministic complexity. And there we have a huge gap. Upper bound of log cube n, lower bound of log star n. Our work does nothing to resolve it. This is obviously the very interesting open problem, and perhaps the most interesting in distributed graph algorithmics. And secondly, now that we've been able to solve this problem, it might be time to tackle harder problems that are even hard to do in a sequential setting, or non-trivial to do there. With that, I stop, and thank you for listening.